Hi, I'm Morgan McGuire from NVIDIA and Williams College, and this is Peering Through a Glass Darkly at the Future of Real-Time Transparency. This was originally presented at SIGGRAPH 2016 in the Open Problems in Real-Time Rendering course. I'd like to thank Aaron LaFawn from NVIDIA and Natalia Tatarchuk from Bungie for inviting me to the course and arranging it, and David Lubke at NVIDIA for inviting me to SIGGRAPH. So if you go to any animated film festival, such as the SIGGRAPH 2016 Film Festival, what you see are a number of really impressive short films that have, for offline rendering, absolutely beautiful transparency effects. Unfortunately, they're also kind of a catalog of effects that we can't render in real time. So for example, the subsurface scattering in skin, the thin objects like blades of grass and hair, the participating media where the light is passing through fog and lighting it up and scattering, anything like rain, and of course, water and glass. If we take another look, in this case at a real photograph instead of a rendering, there are a number of effects that we collectively call transparency in computer graphics. These include things like the partial coverage from the thin blinds, where every individual object is less than a single pixel, as well as effects like depth of field, where because of the lens on the camera, the edges of objects that are out of focus become slightly transparent, and of course, classic effects like partial coverage by smoke and things like lighting and shadowing. Here's a partial listing of some of the effects that we call transparency in computer graphics, and I want to point out, again, some that didn't appear in the previous images, such as if you have colored glass and light shines through it, not just the glass has to be transparent, but the shadow itself has to fade out and be colored appropriately. And then, of course, we also have effects for video games, such as magic or force fields, that are transparent emissives, sort of like lightning, but a little bit more complicated and need artist tuning. And one of the classic effects is also edge anti-aliasing. So if you look at all of these effects and we try to define what is the transparency problem, how do we formally frame transparency so that we can solve it in a scientific and engineering manner, there's a problem in that all of these effects seem really different, and it's not obvious how we should collect them together. When I tried to come up with a definition for this talk, I talked to a number of people in industry and academia about what should the definition of transparency be. And at first we came up with something that sounds reasonable and describes those effects, but actually doesn't give us much insight, which is transparency is multiple primitives contributing to one sample, or one pixel if you have one sample per pixel. And the problem with this definition is that it's not specific enough so that we can actually solve it. And there are many cases where primitives, say for indirect light, will affect pixels and samples that they're not projected over. It doesn't tell us much about the underlying physics and where we should look for what's correct. And it doesn't, even though it has the word sample, tell us much about how sampling theory applies to this. So instead, we went back to the drawing board and realized transparency is actually two completely different core phenomena. And that if we understand each of those phenomena, all of the other effects suddenly become obvious where they're coming from. And what these two phenomena are is transmission and partial coverage. So in this photograph, on the left side, you're seeing a red theater gel. And on the right side, you're seeing a red scarf. The theater gel on the left is transmitting light. So light is passing through the medium of the gel and interacting with the medium. And that creates effects that we call refraction, diffusion, extinction, chromatic aberration, and many others. If you look at the shadow from the theater gel, you'll notice that the shadow is tinted red. On the right, we have partial coverage. Partial coverage is where the actual primitive has varying coverage within a pixel. So it's either there or it's not, but in some pixels, they cover a large swath of the material, and it might be the individual threads are passing light through in some cases. Note that the shadow is gray. There's no diffusion, no refraction, and the background is not colored. It's just a blend of the color of the foreground and the background. And an easy way to know, as a thought experiment, which of these two underlying phenomena you're looking at is ask yourself if you had a red transparent surface over a blue background, what color would you expect? If you have transmission like the theater gel, red over blue produces a net black because none of the blue light can pass through the red barrier, and there was no red light coming off the blue surface. If you instead have partial coverage, what will happen, as in the case of the scarf, is that if you have a red scarf over a blue background, about half of the blue light actually passes through the holes in the scarf, half of it's blocked and then replaced by red light reflecting off the scarf, and so you get purple. So if the colors are blending strictly in sort of a color blending sense, you get partial coverage and you'd see purple. And if it's transmitting through the medium, it's actually filtering out light, and you would get black if you had two radically different wavelengths. So here's the structure of the rest of the talk. We framed the problem as transmission and partial coverage. We'll go and look at each of those in detail and see what's the physics, the computer science, the sampling theory behind those. Once we understand the sources of these phenomena, we'll look at what are some current strategies people are using today effectively for transparency. How do they break down into broad categories? And then which of those is a good idea for pursuing in the future? Some are great for today's hardware, but they might not be a good direction for future research in terms of scalability or converging to a correct solution. So let's start by framing the problem by looking at transmission. And transmission is a real phenomenon. It's dictated by physics. It's hard to solve in real time. It turns out it's even hard to solve in offline rendering, as we'll see in a moment, but it comes from nature. And I'll start by telling you the ray optics of transparency. And there's going to be a little bit of a footnote, which is that in rendering, we typically make some assumptions about physics. We assume we only care about steady state light transport. We don't look at individual photons. We look at what happens in aggregate. We ignore some properties like phase and polarization. So in almost all of the cases that we care about, at least for entertainment applications as opposed to predictive rendering, these simplifying assumptions are reasonable ones. If we're satisfied with the kinds of images we're getting in film and we just want those faster, these are good assumptions to keep for the moment. So we start with a ray of light. An array of light is always transmitted through some medium unless we're in outer space. So in this case, we'll say we're inside of air. Air is our medium, and interesting things happen when we transmit into a different medium. So I'm going to put orange gelatin because there's a classic in-joke in computer graphics about Jell-O brand gelatin, thanks to Paul Heckbert. So when the ray of light hits the orange gelatin, we've moved into a different medium. And at that point, as you know, two interesting things will happen. One is that the ray of light will change its direction because of the varying index of refraction, and so we'll see it bend the light at the interface. The other thing that happens is as the light propagates through the medium, all of the not orange light becomes gradually absorbed. And it's important to know that the light isn't absorbed at the interface between air and the Jell-O. It's as the ray enters, it's still white light, but then all the other wavelengths start dropping out as they become selectively absorbed. And of course, we also get reflection off the surface of the Jell-O, so we can see reflections of the scene behind us. Everything that happens there is described by the refractive index. Now, this isn't the refractive index that at least I learned about in high school. This is the complex index of refraction. It has a real part called eta and an imaginary part labeled kappa, and each of those varies with wavelength. In practice, kappa is actually not statistically independent of eta. There's extremely complex theory describing how in some materials you can derive one from the other, but these are properties that you can look up, they're easily measured, and we're just going to start with those as the two pieces of the model. And let me show you how all of the effects that happen can be described using these two properties. So we're going to take air, and we'll label that. Air is a nice medium to be transmitted through. It has an index of refraction that's close to 1 in the real part and close to 0 in the imaginary part. So it's kind of slammed against the bounds. And what distinguishes orange gelatin, now the orangeness is coming from the wavelength variation, which I'm not going to notate for the moment, is that it has a different index of refraction. In fact, when we say that light travels along a straight line through a homogeneous medium, what we mean is optically homogeneous. And what optically homogeneous means is that the index of refraction hasn't changed. So really the only difference between these two is that when we enter the Jell-O, we now see a real index of refraction of 1.4 and an imaginary one of about 10 to the negative 6th. And what's perhaps surprising, or at least it was to me when I was preparing the talk, is that there's actually data on this on the internet. So really, even for everyday materials, we can measure these directly. And if you think about the complex index of refraction, it turns out once we see the equations for absorption, you can actually guess within about an order of magnitude what these numbers should be. So our first question will be, what are the angles? Well, the measures of the angles of incidence and reflection are easy. They're just the same. So that's mirror reflection. So those two theta 1s are the same. And then if we look at the theta 2, that's going to be given by Snell's law. Snell's law says that if we take the ratio of the real parts of the indices of refraction, those are related inversely to the sines of the angles. We also want to know how much of the light is going to be reflected versus refracted into the medium. And that's given by the Fresnel reflection coefficient. The full model of it is actually not that complicated. It has a lot of terms in it, but if you look at them, they're all cosines, which means in practice when you implement this, they're just going to be dot products. But there's a common approximation that's used in computer graphics, thanks to Christoph Schlick, and that's shown on the bottom of this slide. So we can drop in that equation. The only thing that matters for the moment is noticing that this equation only depends on the angles, which depend on the indices of refraction, and the index of refraction itself. So again, everything is parameterized solely on index of refraction of the medium. There's no notion of colors and scattering functions and all the other complexity we're used to bringing. Of course, there's one constant hidden in here, which is that F0. And the Fresnel coefficient, F0, is of course given by the indices of refraction. Again, don't worry about the exact equations right now. You can always look at them later. The key idea is that everything in our derivation, how much light, what directions, is all given by that. So as the light travels through the medium, we come to every undergrad's favorite law, which is the Beer law for absorption. And this describes how fast that white light was getting absorbed with only the orange light propagating through the medium. And it says that light falls off exponentially. So if we write this in terms of radians, here's the exact expression for what happens. So we have a point x, a point y, and the extinction coefficient, kappa, the imaginary part of the index of refraction, is the key variable, and that's what's controlling it. So kappa is telling us how fast light falls off, and that's why it's relatively easy to estimate. If we know that our wavelength is around, say, 500 nanometers for visible light, we can estimate, well, what should the exponent be? What does kappa need to be in the numerator to make the exponent such that we observe light falling off? And if you look at Jell-O, you can see through maybe 4 or 5 centimeters of Jell-O pretty well, and then it starts to get more opaque. And so from that, you can estimate it better be about 10 to the negative 6th for kappa to make that work out. There's also one other effect that I haven't described that's a little bit more complicated, which is multiple scattering or in and out scattering. This can actually be derived from the indices of refraction. There's often a diffusion constant that's parameterized as well for the material. But what this says is that while the ray of light is propagating through the medium, sometimes it scatters off individual molecules and scatters out of the ray. And so we lose some light. This is actually wrapped up in kappa. So kappa is accounting for the light loss due to scattering out, but we need to know directions, and that's where the diffusion constants will come in handy. Of course, if some light is scattering out of our ray, some light is also scattering in from some other rays, and so we gain a little bit of light as well. And that's what's called multiple scattering, typically in rendering simulations. So the interesting thing is, that's it. So I've applied our model. I've taken orange Jell-O. All I need to know was its index of refraction, air index of refraction, and that's it. I can derive everything else about transmission from there. It's not that complicated. And of course, since everything is parameterized solely on the index of refraction, if I change the medium, I can do so, say, to water just by changing the index of refraction. Or I can do flesh. And you might think, wait, is flesh transparent? You can't see through me, hopefully. But if you take, say, a flashlight and you hold it behind your ear, if you have a thin enough piece of the human body, you can see some light through it. And it turns out flesh has conveniently been parameterized by an index of refraction you can look up on the internet. And so you can simulate all of the complex subsurface scattering effects and light traveling through earlobes and fingers just by plugging those constants in. And in fact, let's go to a harder material like brick. Now again, this is a transparency model, and your first reaction might be, is brick transparent? And the answer is, it is. So if you think about, say, visible light, obviously it doesn't go through a thick amount of brick. But remember that, as with the jello, the light wasn't absorbed immediately on contact. So the non-orange light took a little ways to go. So if you have a thin enough slice of a brick, you can actually have a brick window. If it's curved, you can even make a brick lens, because it has a nice real part of the index of refraction of 1.8. And if you don't believe me on this, also think about why there's data on brick or other building materials. Why are people computing the indices of refraction? And the answer is, computer graphics people aren't, but say people who model Wi-Fi signals, which are just another form of electromagnetic radiation, want to know how fast it'll propagate through brick and how it'll be refracted, or through wood. If you think about X-rays, there are obviously materials to which visible light is opaque, but which X-rays travel through. And another great example is UV light. So it's coming from the sun just like the visible light, but we know that a window will block UV light, or sunscreen, even though they appear transmissive to visible light, they're opaque in another wavelength. So that wavelength dependence is really important. But the same model can be applied to all materials. There is no special notion of transparent or not transparent. This is really a model for all materials. In fact, I can even apply it to conductors and things that you would normally think of as purely reflective, like aluminum. So the transparency model applies there as well. Of course, kappa is really big. So the extinction coefficient, recall for things like water in jello was around 10 to the negative sixth. It's a million times larger, 6 orders of magnitude larger for a metal. Light is absorbed very quickly in the visible spectrum as it enters a metal, but it is actually transmitting a little bit of the way through. And what that tells us is that this wasn't really the ray optics of transparency. The model I've just described is all of rendering. That's all of ray optics. You don't need a special model for opaque surfaces and a separate one for transmissive. So we have optically homogeneous media, and that's what defines a material. Our notion of a surface is really just the interface between two different homogeneous media. We can apply the Beer-Lambert law within the medium to find out how fast light falls off, and if the extinction coefficient is very high, the surface will appear relatively opaque because any normally occurring thickness will block almost all light. And we can compute reflection and refraction by just applying the Fresnel-Snell laws at interfaces, and we need some model of multiple scattering. So our only parameterization is just a function that tells us at every point in space what is the index of refraction, and we can run all of rendering. And in fact, there are 3 algorithms that are known in computer graphics that, given that model, can actually render a physically correct image. Metropolis light transport, path tracing, and bidirectional path tracing. So if you run each of these algorithms long enough, they will actually converge to the right answer, and you don't need any of the complexity that we typically associate with computer graphics algorithms. The problem, of course, is that applying those on very small pieces of geometry and very dense media that change frequently, say like smoke or clouds, it takes a really long time to converge. In fact, it takes so long to converge that even for offline rendering, for film, people don't use these models directly. What they instead do is they start to abstract and talk about aggregate pieces of surfaces. So what we know is the bidirectional scattering distribution functions, so the BRDFs and BTDFs and so forth, are really just a way of saying, instead of modeling what happens with the refraction and reflection at every individual little plane of the surface, let's talk about small patches and what the aggregate scattering is across them. And that'll allow the model to converge faster. Let's not really do transmission through surfaces with high extinction coefficients and high diffusion. Let's model that with, say, Jensen's scattering distribution function. And if we're traveling through a medium that's very complex, so if we have smoke in the air, we're constantly changing between the index of refraction for smoke and the index of refraction for air, then in that case we could use something like photon beams to aggregate what happens to the light along a relatively thick path as it goes through there. And we've incorporated a lot of these ideas into real-time rendering as well, but the key idea is that the offline rendering algorithms are extremely stable for transparency phenomena because they can ultimately process rays and sample them as they wish using these 3 really stable, physically correct algorithms. So that's transmission. There are offline algorithms for it, it's physically based, but probably those algorithms aren't going to converge for real time. And part of the problem is that even for film, effects like multiple scattering are just too complex, and they'll tend to fake it by just adding extra lights inside of a cloud or inside of smoke to account for the missing light that wasn't multiple scattered. So this approach of directly sampling the function gives us a lot of insight, but it's not a good path forward. We'll see paths forward for transmission in a moment, but first let's step back and cover the other half of the transparency problem, the partial coverage phenomena. And I'm going through all of this fairly quickly in the slides. You can find lots of details both in the offline PDF version of this talk and in the graphics codex, which is my low-cost computer graphics textbook that covers all of the physically based ray tracing and rendering. So now we'll move on to partial coverage. Unlike transmission, partial coverage is not a naturally occurring phenomenon. It's because when we chose to sample along rays and then use the value along each ray to approximate what's happening across an entire pixel, we took this small point, decided it represented a full square. And of course, that's not the case many times. And so there's a sampling problem that we introduced. There's aliasing. And partial coverage is a model that was developed in the 70s and 80s as a way of fixing the sampling problem. And the problem that it creates is when we go to today's real-time methods, it creates an ordering problem that's similar to what happens with transmission, but is ultimately a different phenomenon. So here's the aliasing problem. If I start with the scene on the left, that's true geometry, and the orange grid is just showing where pixel boundaries are. And if I ray trace that, or if I sample it with a rasterizer, because ultimately all that a rasterizer is a ray tracer that's been amortized to take many parallel samples across a triangle, either of those will produce the image in the center. And the image in the center has all of those jagged edges because there's only one ray per pixel, and it can't properly account for the pixels that are partially covered since we're only getting binary coverage. What we would like to have is something like the image on the far right. The image on the right has converged. I've cast about 16,000 rays at each of those pixels, and so what we're seeing is an accurate representation of how much of the original little striped bars are covering each pixel. But we would like to get that instead of paying 16,000 times as much, we'd like to get that paying for only one ray per pixel or one ray per sample. So real ray triangle coverage is binary. And if you think about what happens in nature, when there's an interface between two media, a ray either hits the interface or it doesn't hit the interface. There is no notion of it sort of hits the interface. So in the real world, things have to either interact or not. So alpha equals 1, full coverage, and alpha equals 0, no coverage, the ray misses, are physical phenomena. But because we get aliasing, and the aliasing which will manifest as noise, jaggy edges like we just saw, but also temporally as flickering or as blur, we want to introduce this notion of partial coverage. So we just allow alpha, the notion of does the ray hit the surface or not, to be between 0 and 1 as well. And of course, Porter and Duff's classic paper in 1984 laid down a lot of the framework for what we do today using alpha matting and partial coverage. It's pre-filtering for many rays to reduce noise, but it has some assumptions. And in many cases, these assumptions end up being violated and come back to bite us. So things like, we're assuming that the positions of objects within a pixel are uncorrelated. So if we have a series of columns in an architectural building, and we're looking down the series of columns, and we're looking at a pixel that's exactly halfway on the column and halfway off, well, all of those subsequent columns line up behind each other. Those positions are correlated. So the net partial coverage should be 50%, but if we blindly assume that they were uncorrelated, we might end up with a coverage that's 99%, which is incorrect. And partial coverage also assumes that visibility is independent of shading, which in many cases is not true, and the two are related. There are many causes of partial coverage. The classic one is just edge anti-aliasing. The primitive is actually covering half a pixel. Of course, the primitive might be itself less than a pixel wide. We have textures that are representing fine geometry that we're going to represent by just an image, and those have alpha channels. The alpha channel would naturally be binary, so if we have a tree leaf, it's cut out in the shape of the leaf, and every texel is either on the leaf or off, but when we compute mipmaps, we get partial alpha from that. As I mentioned at the very beginning, depth of field and motion blur, although these occur due to the mechanics of how cameras work, because of the computer graphics model of the image plane actually being in front of the camera, we get aliasing from rays either moving in time relative to objects for motion blur, or depth of field, the rays that go through a single sample could have multiple origins because they're hitting different points on the lens. And of course, the number one cause of partial coverage and real-time rendering is actually the fact that since in many engines we couldn't afford to give artists a true model of transmission, the artists faked transmission using partial coverage. So these should be separate phenomena, but if all you have is one tool, the artist will use that to approximate glass by what would physically be a thin mesh instead of an actual piece of glass. So what Porter and Duff told us is the primary compositing operation. Say I have a situation where I'm looking from my eye on the left, in the foreground there's a tree, and trees have leaves, so some of the light comes through and some doesn't. We're ignoring the transmission through the leaves themselves. So there are little holes, some of the light comes through, there's partial coverage by the tree, we'll call that alpha sub A, and in the background there's this opaque mountain. Under that model, the equation for combining the light from the background with the partial covering foreground is simple. It's just linear interpolation. This is called the over-compositing operator because it's modeled in terms of knowing the coverage of the foreground and having already accumulated what was behind it. There's something called the under-compositing operator that's effectively the same equation but parameterized differently. And then other ones based on different assumptions about how the coverage is correlated, the subpixel positions of objects. Now, the key problem with transparency, obviously linear interpolation is not an efficiency challenge, is that it's order dependent. So we can't composite these surfaces in any order that we wish. We have to start from the back if we're using the over operator and render back to front. So if we look at each of these individual terms, you see that we can't just move those terms around because they're nested in different levels of parentheses. This order dependence causes a serious efficiency problem for modern real-time renderers. And that's because every time that we change the blending mode or need to reorder primitives, we have to break a series of draw calls. And when we break the draw calls, we end up with a pipeline bubble where the GPU is not doing anything for a little while. And that causes both a latency and then a net bandwidth problem because we weren't getting our maximum throughput. So if we go back, having seen both transmission and partial coverage where they arise from, to our original laundry list of effects, we can now categorize where they come from. So if we look at the ones that I've circled in blue here, those are effects that are primarily due to transmission. So things like colored shadows, refraction, coloring of the background, chromatic aberration. What's interesting is that although depth of field actually arises from a lens, which is a piece of glass, for the purposes of how we'll model this inside of a renderer, I'm not going to call depth of field a transmission effect for the moment. Very few renderers work by actually inserting glass lenses into the scene in front of the camera. And then, of course, these are the partial coverage effects. And there's one overlapping one, which is that I've put volumetric lights and shadows, so shafts of light and shadow going through fog or mist. I've categorized that as both partial coverage and transmission, and that's because it is. So if you have something like a cloud, the medium is inhomogeneous because we have a mixture of water vapor, ice crystals, and air. So there are different indices of refraction there. But we also have partial coverage by those individual particles themselves because they're all going to be subpixel. They're all going to be distributed much more finely than the sampling of our rays. And so there are different ways of modeling those effects. And since that one is really dependent on multiple scattering, it's in general one of the most complicated volumetric effects to simulate. So now that we've framed the problem, we understand the basis. Transmission is real. All we need to know is index of refraction, and we can do all of rendering. Partial coverage is the sampling problem that arises from using rays, and so we can use that to avoid the aliasing from sampling, but we'll introduce this order dependence problem. Now we can actually frame the solution. And the solution has some constraints on it. We would like a general purpose solution. We'd like to be able to look through a double pane window at a smoky room with a fish tank that's many different kinds of transmissive and partial coverage materials and just have it all composite correctly. We don't want to have to flag water as a special case and glass as a special case and fog and have different rendering algorithms for all of those. So in the limit, that's where we'd like to be. It's also really important to have transparent shadows that are consistent with the visible transparent surfaces. So when we're casting rays from the eye and rays from a light or indirect light, we would like to have consistent results between them, and many of today's algorithms actually don't satisfy that. I've talked a lot about physically based rendering. We like the stability and predictability of physically based rendering, but there's also, for a lot of applications, non-physical rendering that's important. So for example, if the character that I have to be able to track walks behind a rock, I'd like to see maybe a glowing outline of the character. There's no physical reason I can see the character, but it needs to be there. And of course, we need artists to be able to tune effects in ways that are aesthetically valid and that create the net emotional experience they want from the scene, even if that doesn't match any real-world physics. We still do want the robustness and the predictability. I think the most important piece of that is not getting light or dark leaks, especially for game applications. So if there's smoke in the room next to me and a grenade has gone off, if I have no visibility into that room, I shouldn't have light leaking from that room into the room that I'm in, because that would give me incorrect gameplay information. It would be revealing something that's supposed to be hidden information. And we don't want to make too many compromises. So obviously, we'll need to do some kind of shader level of detail and flag certain effects as more important than others on any given platform. But we'd like to have an algorithm that could scale to all glass is reflective. It's not a special effect, it's just a built-in part of the renderer, and so forth. Now, one thing I haven't mentioned so far, and that I'm actually not going to mention too much until the very end of the talk, is the big elephants in the room, which are that the way that modern renderers are made for real time, what makes them fast, is this assumption of at every sample there's a single surface, there's a single depth. It's exactly what fights with what's happening with transparency. So for example, deferred renderers, and almost everybody's deferred renderer actually is a hybrid renderer that makes a forward pass for transparent. Deferred rendering assumes that all the information about a pixel can be stored for one surface. And so there has to be some way, if we want truly integrated transparency rendering, to generalize that more. One idea that I think is kind of out there in the air and a lot of people are looking at is, what if we store a deferred renderer, we have a geometry buffer storing all the properties at every sample, but we let that go kind of deep. So we have a layered frame buffer of some sort, a deep G buffer or K buffer, and maybe to make the number of layers finite, even in the presence of something like smoke, we have to do some aggregation into layers. And Cyril Croissant's aggregate G buffer anti-aliasing is sort of one direction you might go forward for the aggregation. And there's also a huge number of post-process effects. So even if you cast rays, if you did a real ray tracer, for the primary visibility rendering, there's this problem of a lot of the look of modern game engines is based on effects that happen in screen space. Motion blur, screen space ray tracing, temporal anti-aliasing, ambient occlusion. And all of those effects depend on assuming that at every pixel there's a unique depth, unique normal, motion vector, and so on. And that obviously doesn't work very well for transparents, and that's been acknowledged by a lot of the previous academic research. And you can see that these things are happening in modern games because you end up with cases like you have a tree where the interior of the leaves of the tree are opaque, but the edges are being anti-aliased with partial coverage. And when we run the ambient occlusion filter, which makes everything darker, we get nice darkening on the tree leaves, but then the outside of the tree leaves, because they're transparents, aren't represented in the G buffer, and suddenly they start glowing bright. Or if you have a car that's driving, well, the windows on the car are transparent, and so they don't appear in the deferred shading G buffer. And so when you look at the car in its reflection in, say, a building as you drive past, the car has no windows on it. There are many effects like this that happen in real-time games. And the reason that you don't see these problems more often is just that artists are really good with the art direction for hiding them. And of course, there are production constraints for games. There's a huge performance range from consoles, which are DX11, all the way up to DX12 PCs, and PCs themselves have about an order of magnitude variation in net performance. And what's interesting is because video game development and production is really dominated by the art workload. So we might have 20 artists for every programmer. And it's actually reasonable under those constraints to say the programmers will actually redesign the engine for every platform. So it's totally reasonable to have a different algorithm on a different platform, but because they can't afford the art time, it must work from the same art assets. So all models on all platforms have to work from the same input and have to produce similar output. And transparency budgets are, of course, it's not like even rendering at 30 frames per second, you don't have 33 milliseconds to render transparency. You have maybe 4 milliseconds to render transparency because the rest of the time is spent rendering everything else in the scene. When we start looking at really high resolutions and high frame rates and stereo rendering, say for virtual reality, transparency budget might be down around half a millisecond. So this is extreme performance that's needed. And I should also mention, although a lot of the work in transparency talks about game rendering, and it's an important application, there's also non-game applications. So for example, digital content creation probably has some of the hardest transparency problems. They're constantly rendering very thin wireframes for millions of objects overlapping and need really good partial coverage. You can imagine an architect doing pre-visualization will have lots of glass and water and other transmissive objects in a scene that need to be rendered. And there's also hidden surface renderings, like on the right, where the surfaces, we have to be able to see through them for modeling purposes. And this is a really hard case because although it doesn't need to be aesthetically pleasing, the algorithms need to be incredibly robust. Nobody is going to hand tune. We don't know the scale of the scene. We don't know the number of objects ahead of time. A rendering program for something like 3D Studio Max, when you're in the modeling view, just needs to work. So those are the constraints. Now let's see how we can try and satisfy some of those. Before I go into specific algorithms, I want to mention I'm not going to talk about the algorithms that produce the best images today. So game developers with great art direction, really clever programming tricks for specific platforms have created solutions that work really well in some cases for that specific game or that specific scene. For example, Playdead's Inside has, I think, some of the best transparency rendering today. Almost every scene has fog, smoke, water, glass that's diffusing. They have fire in the game, and it's constantly layered. So you'll be underwater, but there's participating media, and there's light shafts, and there's bubbles of air going up through the water, and it's all being lit gorgeously. And this is also one of the first games I've seen that has effectively no aliasing. So they've really solved partial coverage for their game. But although this game is beautiful, and this is exactly how we would like all games to look, there's this key problem, which is that this look was achieved primarily through really great art direction and careful design of individual scenes because they know the fixed camera, they know exactly the content. So this probably doesn't tell us much about where to go forward. The techniques I'm going to focus on now are not necessarily the leading techniques for individual titles, but they're the ones that I think show us the most promise for directions we might want to pursue in the future. Broadly speaking, there are a couple of different strategies: sorted transparency, ray tracing, and so on. I'm going to go through each of those and give some citations for papers that I think are sort of a leading place to look. Sorted transparency is probably the #1 way that transparency is handled today. And it's unfortunate, and this is the reason that we consider this an open problem, because there are a lot of drawbacks. So what's nice is that sorted transparency can handle both partial coverage and transmission. So we just sort the objects back to front, composite them as we're going, and for every surface we need to change blend modes. So if it's a piece of glass, we need to sample the background, distort it for refraction, add in some light for the reflection, and then move on to the next level. If it's partial coverage, we can just do that alpha blend of linear interpolation. Unfortunately, sorted transparency only works for compositing what the camera can see. It's effectively useless for shadows and indirect light. This isn't something we can apply inside of most GI algorithms. It's not something that works well with shadow maps. And as I've described before, because we have to break draw calls to switch blend modes and in order to sort objects, it's inefficient on modern GPU architectures. And in theory, it's actually impossible to sort primitives correctly. So just like you can fold the top of a cardboard box in a way that makes a continuous spiral, you can layer primitives in ways that there is no correct ordering unless you fragment them separately. So this is the forward transparent pass of modern rendering. It's what everybody's using. We need something that's faster and that works for indirect light. So ray tracing, which is what film has moved to, or ray marching, which is primarily ray tracing inside of a volume, is great. It's a bulletproof transmission strategy. It just gives you the right answer. You do have the aliasing problem, but you can model partial coverage, and that works pretty well for ray tracing as well. And it gives consistent results for indirect light and shadows. So the good news is there are 3 different APIs from each of the major processor vendors that all implement real-time ray tracing. And they're too slow for full game rendering today, but they're getting pretty close. So we're within about an order of magnitude of what you could use for game rendering. Those people who've been listening to the ray tracing literature for a while will notice, everybody always has said for the last 4 decades, ray tracing is almost there. We're within about 10x, and in a few years we'll be there. I think we're actually going to be there soon, and it's because if you look at the recent publications, say at High Performance Graphics, all of those vendors are clearly working on ways to either adapt the algorithms or adapt the hardware to make this more efficient to close that gap. And the rate at which GPU performance has been increasing is truly astonishing. It's been near exponential for the last couple of years. So getting that last 10x, especially if display resolutions stop climbing, is actually starting to become within our reach. But I don't think you would use ray tracing for all game rendering. I think if you just use ray tracing for transmission, this becomes more interesting. I profiled all 3 of these APIs recently, and they obviously have different performance depending on the GPU or the CPU, but for all of them, if you took your favorite game platform, so like a PlayStation 4, and you took a second PlayStation 4 and put it next to it, and the second one only had to cast 1 primary ray per pixel, and only had to do it at 720p and 30 Hz, if you filled that second machine with that workload, you actually could ray trace modern game assets today. So if we could only double the performance of the consoles without scaling up the assets or the resolution, we're actually there already. And if somebody was willing to make a next generation console or maybe make a really beefy PC GPU, you can imagine this sort of disruptive technology of ray tracing could actually happen pretty soon in hardware. So that's very exciting, but it's not something we can deploy today. So let's keep looking. There are a number of techniques that I'm going to call low-resolution models of visibility. And in order to describe that, I have to tell you about the visibility function first. So if we go back to our scene where we had multiple layers of compositing, the edge of the crate, the smoke, a thin pole that covers half a pixel, and so on, we can graph a function where the vertical axis will be at every distance along the horizontal axis, how much light from farther past this surface can I see? So it'll start close to 1, close to the top of the graph, because initially all of the light that I'm seeing is coming from something farther back. But then as we start to pass objects, and if I do binary coverage as I pass the first object, it drops off, and I get no light from objects farther back. So that would be binary coverage. But when I model partial coverage, this function gets a lot more complex and interesting. So at first I lose some light to the edge of the crate, but I can see farther back. As I go through smoke, it falls off, the thin pole drops a little, the tree, and then I lose everything after the mountain. And what happened was, starting with Veach and Lokovic, they looked at this function and said, that function there has 2 interesting properties. One is that, well, it's obviously monotonically decreasing, but one interesting property is that it's relatively smooth. So it sort of goes along, and then in some places it changes, and maybe it changes abruptly, but there's only a few interesting places, so there should be some low-order approximation of that. And the second one is that, at least if for visible rays, where I'm looking along the ray, or for really complex situations, it would be hard to tell if there were slight errors in that function, as long as they were sort of temporally consistent. And so that's exactly what these models are going to do. And I mentioned that sort of looking along the ray versus looking at the visibility function for the side, because this is one of those cases where it's really important to have a consistent model between the eye rays and the secondary rays or shadow rays. So for example, in this image, there's fog, there's a sphere casting a volumetric shadow in the fog from the light. And if I cast a visible ray from the camera, that's just sampling 1 point. I'm looking at the visibility function edge on, and I really have no idea if it's right or wrong, as long as there's some partial coverage. But when I look at that volumetric shadow, I'm actually seeing the visibility function as it falls off. I can see how I lose visibility going through the fog, and then it drops off abruptly at the sphere. And so in that case, I need to be a little more accurate. The model of deep shadow maps was the first sort of offline rendering idea of modeling that visibility function explicitly. And what people have since done is introduced a series of techniques like K-buffers and Fourier opacity maps. There are other approximations of just saying, instead of sampling that function densely, can I somehow replace it with a spline or a Fourier series or a few samples? The K-buffer approaches are interesting. These produce a layered buffer for the frame buffer that stores K layers. This is a practical version of the original A buffer for accumulation kind of effects. And what's interesting is they work on this consistency principle. They're not necessarily order independent in the sense of it doesn't matter what the depths of objects are, but they're consistent in terms of the fact that if I submit the same work in the same order, I will get the same image every time. And if the changes are small in the input, the changes will be small in the output. So for modern implementations, what you do is you basically build a little linked list or short array at each pixel of every transparent surface that's been encountered, and then you composite them at the end. And there's an extreme version of this that's mentioned in Salvi's 2014 paper, where you can actually go down to a single layer. So the K buffer, in a sense, is not layered anymore. But what you do is you store the closest depth to the camera, the minimum depth of whatever the last surface was. And when you get a new surface, if it comes behind, you under-composite it. And if it comes in front, you over-composite it. Then you can change the blending mode based on the depth test. And you have to do that using pixel shader interlock. One slightly older version of the K-buffer that I want to mention because it's still relevant is Mall's K-buffer, which does really nice effects for hair and other partial coverage things. This doesn't really do anything for transmission. Is implemented using solely atomics, which means this can be used on consoles today. If you have access to a DX12 or better platform, of course, the modern implementation of a K-buffer would be to use Salvi's approach, where it's using pixel shader interlock. And what happens there is that we actually can insert a barrier into the pixel shading, load up the little list, do an insertion sort into it, accumulate the final layer, and then write it all back. And this is the best technique I know of today, specifically for handling the partial coverage of hair. So this gives really good rendering of hair, and I don't know anything else that gets comparable. There's another line of thought for a low order implementation of the visibility function, which is order independent blending. And the idea here is instead of storing those samples, if you're bandwidth constrained, what if we just completely hallucinate the visibility function? So what if we guess about how that visibility function fell up with depth rather than storing things? And what's nice about this is because it has a single layer and it's just guessing all the other layers, you're able to model colored transmission efficiently in it, as well as partial coverage. And this works on current hardware because it only depends on existing alpha blending and multiple render targets. And there's some screen space tricks that you can inject that allow you to do refraction and diffusion, which is what the phenomenological rendering paper is about. So these are real-time results showing on the top diffusion and the bottom refraction. And you can, of course, mix low-resolution particles and refraction, diffusion, glass, and different materials together. The results for this, because it's approximating, often using something like the Beer-Lambert function for assuming how's the visibility function going to fall off in space, is that for certain kinds of low partial coverage, for example, the hair case, it doesn't work as well as the K-buffer approach, but it can be higher bandwidth and faster. And then is stochastic transparency. Stochastic transparency, at least with a traditional frame buffer, only covers coverage. So it doesn't do transmission. You can't do refraction and things like that with it, but it's bulletproof for coverage. And it's bulletproof because it basically takes partial coverage and then turns it back into binary coverage at multiple samples. It works well for indirect light and shadows. In fact, this is the best technique I know for handling shadows through transmissive media. And it unfortunately requires really high sampling rates because the whole point is we need a lot of binary samples to accumulate back to the analytic alpha. There's some techniques so this is used in practice today in very specific cases where it's very effective in games. Kirshner's inferred lighting paper has been used pretty widely, especially for things like level of detail transitions, as well as some cases like glass. So what you're seeing here is this is interleave shading for partial coverage. And of course, this is a helicopter cockpit. It should have glass, but this is one of those cases, like I said, where artists are going to use partial coverage because it's the only tool they have. And on the left is the image that's rendered. And so that's what's actually happening in the geometry buffer. And there's basically this dithering of pixels can either store the glass surface or what's behind it. And it does it in a very specific known pattern. And this works really well if you have, say, 0, 25, 50, 70, 100% alpha. It's not as good for arbitrary ratios because the dithering patterns get a little strange. And what you see on the right is the final image presented to the viewer. And the reason that image looks good instead of dithered is since we knew the exact pattern of putting things in the foreground and background, we can reconstruct what should be the blending at any pixel, and we can look in a small area to get the average values and write out the actual underlying alphas in them as well. So that works really well, and that's used in a lot of deferred renderers for certain kinds of transparency effects. Here's the dream renderer for PlayStation 4. Ignore the volumetric effects of the light for a moment. What I'm showing you here is that all of that partial coverage on the grass and hair is being handled by just doing binary coverage at 1 sample per pixel, and then a really good anti-aliasing pass at the end to blend out all those fine details. This works well for this particular game because it has this very impressionist style, and a little bit of over blurring and a little bit of flicker is going to be okay. But this is a nice use case showing that, hey, maybe if we had really good 8x MSAA or 2x MSAA, but a really good post-processing anti-aliasing filter, we could actually get away with going back to binary coverage. And in fact, many deferred renderers, at least for edge anti-aliasing, have now moved to temporal and post-filter anti-aliasing, and they're doing 1 sample per pixel stochastic anti-aliasing. I also mentioned it's the only technique I know for getting really good shadows from transmissive objects. So in this case, this is the stochastic variance colored shadow maps. And you can see the purple shadow from that water bottle, or you can even get caustics. And in cases like we said, where you see the visibility function from the side, so the light shaft that's passing through the Lucy angel is white before the angel and blue afterwards. And this is all being done with a shadow map that's storing stochastic depths in it for each color channel, and then with a variance shadow map computed on top of that to do the pre-filtering. A really interesting presentation from Chris Wyman this year at HPG 2016, which also won the Best Presentation Award, showed that actually the ideas of layered transparency from things like K-buffers and stochastic transparency are actually different points on a design continuum, and that he introduced an algorithm that unifies them, where he can choose stochastic samples, but then he can also choose to put them into different layers, and he corrects for all the probabilities as he goes. And this creates a number of different points where you can trade off between noise and bias in the algorithm. I also find this approach very interesting because it combines the bulletproof stochastic transparency for partial coverage with the layered transparency that you're going to need for transmission. And so I think this is a really exciting direction to pursue in the future, and I think we're going to see a lot of work following up on that. All of those were for primarily cases where we had hard surfaces, where there was a simple interface. For volumetric effects like smoke and clouds, there's some really nice algorithms that have been developed specifically for skies, where there's all kinds of volumetric and complicated scattering. And those, kind of like with Inside, are beautiful and are the state of the art and are what you should absolutely do for rendering skies in games today. But they don't necessarily tell us how to render general unified transparency. So these effects make assumptions like the camera isn't in the sky, or the camera is not moving through a cloud, the characters aren't moving through the cloud, that the only light source is going to be from the sun. And those assumptions aren't going to work well when we get to other kinds of transparency. There are some analytic solutions you can make where you know the light cone, you just compute the analytic integral of light, and you put a little noise on it to disguise the perfect cone. So that's used in dreams. That's what did the volumetric shadows there, and that's used pretty widely in games. But there are a number of voxel approaches that I think demonstrate a more robust and physically based way forward. And so the voxel approach is we make a grid throughout all of space. Frequently that grid is distorted so it's in camera space rather than in world space. And then we can actually march a ray through that space just like a film renderer would do, but at lower resolution. There are some techniques. Hugh Bowles demonstrated a kind of shader toy prototype, so this isn't production ready, showing that when you do that ray marching through the volume, you obviously get aliasing not in XY, but in Z. There's aliasing in depth because we're skipping very far. And that while we can't necessarily get the correct answer, we can hide the artifacts that arise from aliasing, hide the flickering and the noise, by making the places where we put those samples move with the medium itself. And so the samples, kind of like a micropolygon renderer does for surfaces, are tied to real locations on the object rather than arbitrary locations in space. I think there are great directions that you could go forward with this if we could somehow vary the voxel slices along each sample. Some of the best work, though, to date, and what I think is quite possibly the framework for future unified transparency for things like glass and water as well, is Hilaire's volumetric work in the Frostbite engine. And what's interesting is that this does really great sort of low resolution volumes, things like smoke and clouds. It's based on the real physics. So where we started with the index of refraction being the only parameter with some additional diffusion constants, that's exactly how this is modeled. And it's storing in each voxel all those properties, and it's doing some clever ways of aggregating the ray march and reusing the ray marches. This isn't ready for deployment yet in every solution because it's not robust. There are some problems with light leaks, with energy going through walls because the voxels don't conform to the surface. And it's right now depending on a very low resolution sampling, so it doesn't scale well. But this has a real physical basis, and it's been demonstrated in important use cases for games to run fast enough to actually deploy for real-time applications. So I think that's a really solid base to build on. And then there are some extreme special cases where I don't actually see us using a generalized algorithm in the future. And these are things like human faces. We're very sensitive to errors in them, and they don't interact much with other transparents. So it's not like I can see through an entire human head. So if I have a special model for the head itself, I can then treat the head as opaque with a special shader on it. And the best place to look for this is Jorge Jimenez's work, which has since been picked up by Brian Karras and some more work. Absolutely gorgeous effects for human faces, special treatment of reflection, refraction, absorption, local shadowing inside of eyes, subsurface scattering in the skin, even effects like you can see through that earlobe when the light's coming in from the back. So this is absolutely beautiful work, the state of the art. I really don't think in the next 5 years we're going to get much past this, and that we should be looking for general solutions for other media, but we might have to special case humans. Likewise, there are a number of effects that are post-processed today, and I think are going to be post-processed tomorrow as well. And a big part of the argument for that is the post-processing is really fast and really good, and that it's what film uses. So film rendering actually does motion blur and depth of field, not in camera most of the time, but as post-process, and as well as things like bloom and lens flare and vignetting. Again, Jorge Jimenez has sort of the state of the art on that. There's some really nice work for motion blur that's used in Call of Duty Advanced Warfare, as well as depth of field effects. And these just work well enough as a post-process, and they work on top of deferred shaders and things. I think we should stick with that. Here's the bloom. Now, don't read too specifically into this chart because it's a very coarse categorization, but I'm trying to get some insight about how all those categories of effects that we looked at so far, how do they stack up in terms of rough properties? So on the horizontal axis, I'm showing you performance. Does it run on a console? Does it handle partial coverage? Can it handle thin and thick transmission? Can it handle shadows and caustics? And is the result actually correct if you turn the constants up? And as we look across all of the techniques, the bright white check marks are cases where it satisfies that column. The gray check marks, it satisfies it in some cases, or it has some performance problems maybe. And where it's empty, that technique simply doesn't work for that kind of effect. We see is that in the short term, we're already using sorted transparency and hopefully transitioning away from that to weighted blending and K-buffer approaches. That all of the things we care about in the short term, performance, current generation consoles, those are satisfied by the techniques near the bottom. And that if we start looking for, well, but is it actually correct? Does it handle all of the cases I need? Those are the techniques that I've put at the top. And so I see in general the industry transitioning over maybe the next 5 to 10 years from techniques near the bottom to looking at things at the top as an overall strategy. Now what I'll do is go into a research agenda. So differing timescales, if you're going to ship a game, so you're starting today in pre-production, you're going to ship the game maybe in 2 or 3 years, what would I look at as new techniques to pursue for pre-production? And this isn't a recipe for saying these are the things you should use. I'm saying these are the things that I think you should start from to try and invent the next level of the solution. And then also, if we really want to solve this, so we're looking 5 or 10 years out, if you're doing an academic research project or a PhD thesis, what techniques do I think you should be looking at there? And it's a very different set. So in the near term, let's look at a 3-year window. I think for transmission, and this, recall, includes effects like diffusion, refraction, chromatic aberration, as well as color shadows. We're going to keep using sorted transparency in many cases for a while, and we're going to keep using screen space raycasting. Those are extremely efficient. They scale down really well, in some cases even to mobile. There just aren't that many opportunities to move past it. I think the best approach for adding robustness to distorted blending and getting some more performance out of it is probably phenomenological transparency. It adds in a lot more effects, and it gets rid of those pipeline bubbles and allows you to do variable resolution. That's for transmission. For partial coverage, so cases like smoke and thin objects, the hidden surface rendering or the mip-mapped alpha, if you have access to DX12, I think K-buffers are probably the most aggressive technique, and that's a good solution. Like I said, it gives gorgeous hair, it handles partial coverage really well, and it scales down in some cases even to a single layer for the K-buffer. And we've already seen that deployed in a couple of AAA games on PC. For current gen consoles, you simply don't have access to the techniques except for maybe using atomics with Moll's technique to do a K-buffer. And so I think, again, phenomenological transparency is good, and if you're using it for transmission already, it combines really effectively. I think what we're increasingly seeing is that for deferred shading, edge anti-aliasing is handled really well by a lot of screen space anti-aliasing techniques, and then we're not modeling that as partial coverage anymore, and that takes it out of the whole transparency transmission problem. For dense media, Hilaire's technique, which is based on Voss's parameterization, voxels seem really good. Ray marching voxels, and in some cases using either dense particles or particles injected into voxels seems like the way to go. I would probably take Hilaire's approach and then look at ways of increasing resolution and avoiding the light leaks as a near-term research. I would stick with Jimenez's approaches for both human faces and for all the post-processing. So that's production. But what if we really want to solve this? Where are we going to go if we're not constrained by having to support current generation, either PC GPUs or consoles? So if we look at a decade at a research target, I think we're absolutely going to switch to ray tracing. Not for all rendering, but I think for transmission, it's such a robust solution. It handles all of the effects, ray trace the triangles, ray march the voxels. It just works. The only problem is we need a little more processing horsepower, but it's not a ridiculous amount. So I think we're just going to see that happen. The key idea for the research agenda is, I think it'll happen, but I think you need to invent it for it to happen. So we need to see new hardware architectures designed around ray tracing and both BVH building, BVH refitting, tree traversal, and then ray triangle intersection. And also some support for doing things like ray marching through voxels or sparse voxel octrees. I think we need special support for that in hardware. And then we need algorithms designed for both current and future hardware. So most of the speed up in rendering has not come from hardware advances. The hardware advances have been fantastic, but the algorithms we're using now are a lot more sophisticated than the ones we had in the 1970s. We need more algorithmic speedups than we have now. We need to keep going with that approach. For partial coverage, I also think it has to be either stochastic transparency or a layered G-buffer of some sort. The K-buffer stuff isn't scaling well enough for deferred rendering. And so in order to put everything in integrated renderer, we need to take the idea of a K-buffer, but it needs to be a full-blown K-buffer of G-buffers. Or we need to just bite the bullet and go to stochastic rendering, which gives us the right answer and handles all the indirect rays as well. The key ideas here are we need really good noise filters, or we need really good super sampling. And that can be attacked on both the hardware and the software side. We've seen huge advances in anti-aliasing filters. I think probably the same kind of advances can be made for denoising. And if not, I think there are a lot of clever things like MSAA and CSAA where there are ways that we could do super sampling without paying the full cost. And Krassen's aggregated G-buffer is one great example of that. Regardless of how the primary rays are rendered, I think they need to output to a layered frame buffer. So you can call this a forward plus or a G-buffer, but basically we need to have multiple layers. Now those layers might not be used for the visible rays. We might have outputted a correct value for the visible ray from the ray tracer, but we still need to produce the layered G-buffer because that's what we feed into post-processing. And if we look at film, I think this is another good place to look for what will be good enough on quality. So the techniques used in film aren't always the ones we want to use in real-time rendering, but I think they're a good quality bar. And if you look at all the sort of VFX breakdowns that you see at SIGGRAPH or now on YouTube on the web, you see that film renders K-buffers. They do compositing. So to build up a frame of a spaceship, you start with a frame of a farmhouse with some smoke in the background, and then you start layering buffers on it. And notice that that spaceship, when it's composited in, is actually aggregating a lot of depth. So the back of the spaceship has different amounts of fogging from the atmosphere and a desaturation falling off. It's being composited as a single layer so the post-processing can work. And then you build up all the layers until you get the final frame. So if film was effectively using hand-tuned K-buffers, I believe that some kind of automated layered G-buffer is a really good approach for real-time rendering. And of course, we need those denoising filters, we need anti-aliasing, bloom, depth of field, and I think just like film does, we're still going to be doing all those in post in the future. Of all those effects, there's one that's actually really important to consider doing in camera and actually rendering correctly, and that's motion blur. And the reason is that unlike all the other effects, motion blur has this problem of it depends on knowing the motion of an individual object at a pixel, and that the phenomena that we see due to shading might be different. So if there's an airplane flying past very low and very fast, then it's easy to say, well, we can post-process and blur out the airplane because it has a motion vector, we know it's moving fast. But if we then look down at the ground and see the shadow of the airplane, there's nothing in our layer G buffer that's going to have velocity for the shadow because it's a shading effect, it's not the actual object. So to have that shadow properly blurred, stochastic motion blur is the only way we know of to do that. So I think there's some interesting research still to be done on stochastic motion blur. The other effects, I think, just like film finds them good enough, I think we're going to find them good enough, and that when we feed them layered G buffers, the limitations that we see in, say, current depth of field will go away because we can see slightly behind objects due to those layered buffers. And the one big caveat to this research agenda, so this is my advice on how I would pursue working on these effects in the future, is that every single technique on this slide increases latency. So it increases the delay between when you produce an input or when you submit work to the GPU and when the final image shows up on screen. And for virtual reality and augmented reality, latency is a huge problem. That's what gives people motion sickness, that's what breaks the illusion. And so the notion of we're going to render everything in multiple passes and mix ray tracing and rasterization and make these post-filtering passes and denoising, that's going to increase latency on the entire pipeline. So in addition to the advice I've given here, I'm going to put one big caveat, which is that the field of low latency rendering is largely unexplored. And I think it's possible that you could subvert this entire research agenda and go in a different direction and say, I'm doing low latency transparency rendering. What's the set of techniques that are going to work for that? And it might be very different than everything here. I'd like to thank again Natalia Tatarchuk, Aaron Lafon, Chris Wyman, Marco Salvi, and Ward Lopes, all of whom helped with the talk. Sebastian Hilaire from Frostbite. Off the end of these slides is a long bibliography that you can look at, showing both the full citations for all the techniques that I mentioned in the talk, but then other ones that I think you should be aware of if you're looking at different kinds of research. Thank you very much.